This is a quick video to clarify the concept of radiance. So what you're looking at here is Dulles Airport, and I have one 30-meter pixel drawn on the tarmac. And so the idea is we want to be able to measure the amount of energy coming off of that pixel, either energy that has gone down onto it from the sun and is being reflected out, or just energy that is being emitted. It doesn't matter. It's just energy coming up from that pixel. We want to be able to measure it in a consistent manner. So for this exercise, we're going to take this two-dimensional pixel that exists in our three-dimensional world, and we're going to translate it into a one-dimensional pixel in a two-dimensional world for simplicity. So we're going to be looking at a 30-meter pixel like this. Okay, so we've got our ground here, and we've got our 30-meter pixel. Now, as we've talked about previously, we can be measuring the energy leaving that pixel from an airplane sensor or from a satellite sensor. And we want to be able to measure the same surface reflectance properties regardless of where we are. So in this case, let's just say for simplicity that this distance is 1,000 meters and this is another 1,000 meters. And so while we've said previously that irradiance in the 3D world decays with the square of distance, in the 2D world, it just decays with distance. So there's no square. So I'll show you that right here. So we've got our energy that is leaving this 30-meter pixel, and the energy is spreading out. And so let's say we had 100 watts per meter here. Remember, per meter, because we're in a 2D world right now, not per meter squared, but it's the same idea. So 100 watts per meter here, and that spreads out to be 50 watts per meter up here. So that won't do, right? Because we're seeing different amounts of energy at the satellite that are not related to the actual properties of this tarmac pixel at Dulles. So instead, what if we consider energy per angular unit? So if this angle here equals 5 degrees in our 2D world, and this was up here was 100 watts per meter, we're going to say that this is 1 meter right here. So therefore, it's still 100, but it's 100 per 5 degrees, or 20 watts per degree. So we're just dividing by 5. Up here, we had 50 watts per meter, but this distance is 2 meters. And so we have a total of 100 watts up there. So now dividing that by 5, we also get 20 watts per degree. Okay, so we're getting somewhere here. So at each measurement altitude, we have the same angular measurement. So the one remaining challenge is that this is energy that's coming off 30-meter pixel. So that's a somewhat arbitrary unit, and pixel sizes can vary. So that's what we also want to standardize and get that down to, in the 3D world, meters squared, in the 2D world, per meter. So our last step is then to be say, okay, well, we have 20 meters per 30 meters. What we really want is 20 over 30, or 0.67 watts per meter per degree. And the same thing would happen here. So 20 divided by 30 to get per meter is going to be 0.67 watts per meter per degree. So we've just established radiance, albeit in a two-dimensional world. And so conceptually, we would just switch to 3D. Watts would stay the same. Meters would be meters squared, so area on the ground. And degrees would be in steradians, which is just that three-dimensional angle. So watts per meter squared per steradian, and that is radiance.